In this example, we are asked to show that if a function given to us from r to r plus is strictly increasing, if and only if its reciprocal function is strictly decreasing. So let's first recall a couple of things. Number one, the set r plus, this is the set of numbers that are strictly positive, right? So r plus is the set of all x in r, the real numbers, such that x is greater than 0. And in particular, since x is greater than 0, then it is not equal to 0, right? So this is our codomain of our function, and 0 is not in the codomain. So this reciprocal function is well defined, no matter what. We don't have to worry about this having a divide by 0 issue, right? And this is because of our codomain that we were given as an assumption here. The second thing is, what does it mean to be strictly increasing or decreasing? Well, let's write it down. So strictly increasing means as you plug in larger points from the domain, the points in the codomain are larger as well. So strictly increasing says this: if a is less than b, then f of a is also less than f of b. Alright, so this means that as you plug in larger numbers, b in this case by my notation, as you plug in a larger number b from the domain, the output f of b in the domain is also strictly larger. So there's no possibility that it's even equal. It's strictly larger here. Alright, and you can probably guess what strictly decreasing will be here, but let's write it down anyway. So strictly decreasing. So this one says that if a is less than b, then what's going to be true? Well, this time f of a is actually going to be larger than f of b. So there's where we get the decreasing. As the input gets larger, the output gets smaller. But again, it can't get too small. I mean, it's getting smaller, but it can't leave the codomain here. So it's never going to be 0. All right, so we have, again, at this point in the course, we have not talked about formal proofs yet, but we know the idea of logical arguments and stringing together logical arguments, so that's what we're going to do here. So let's start with the left-hand side. This is a biconditional. We have to go both ways, right? If and only if. So for the biconditional, let's start with the left-hand side. So this is actually the only if direction. So let's just suppose, so let's let f be strictly increasing. I'm just going to string together some logical arguments that hopefully lead us to the conclusion over here on the right-hand side. And if it's strictly increasing, what does this mean? Well, then if a is less than b, it's just the exact definition that we wrote down here, right? Then f of a is less than f of b as well. All right, what we want to do is try to say something about the function g, right? Now, let's say g of a. We want to know, how is g of a related to g of b? Well, g of a, for one thing, by the definition here, it's equal to 1 over f of a. And again, this is well defined because of the way that the codomain was given to us. So g of a is equal to 1 over f of a, but f of a is less than f of b. Now, because we have taken the reciprocal here in a fraction, as the denominator gets larger, which is what's going to happen here, right? As the denominator gets larger, the entire fraction actually gets smaller, right? So the entire fraction actually gets smaller. So when we make this step right here, this is from our assumption here, right? So this is then greater than 1 over f of b. All right, and again, that's because as the denominator got bigger, the whole fraction, the entire fraction, got smaller. But this is, of course, g of b. Right? So now what we have is, if a is less than b, then g of a is actually greater than g of b. So here's our statement. If a is less than b, then, I wrote now, but then g of a is greater than g of b. And so what can we conclude? Well, I'll go back up to our definition. Thus, g is strictly decreasing. All right, so this is not the craziest thing in the world, but it is a good example of how to string together logical equivalences and use definitions with something that we know about, functions. But we're not done, because we're supposed to prove if and only if, right? So now we have to reverse this argument and go the other way. And actually, it's going to look exactly the same, right? So for part 2, we'll just suppose that g is strictly decreasing. And let's write down what that means, right? So strictly decreasing, comma, so that, I'll say it this way, so that when a is less than b, then g of a is greater than g of b. All right? Then what's true about f of a? Well, f of a is equal to, this reciprocal relationship goes both ways, right? By the way, since f of a can't be 0, 1 over f of a cannot be 0 either. So that means that g is never 0, right? The range of g, so g is a function which takes in, actually, in this case, it takes in, by the way that it's defined, right, it takes in all real numbers, because you can plug it into f, and it gives back positive real numbers as well. Okay, so it's got the same domain and codomain as f. So what does that mean? Well, this must be equal to 1 over g of a, and the argument's exactly the same now, right? If we make the denominator smaller, the entire fraction actually gets bigger. This is by our assumption, right, that g of a is greater than g of b, so 1 over g of a is less than 1 over g of b, but this is just f of b. All right, and we conclude then f is strictly increasing, and at this point we should just conclude the entire proof. All right, we conclude then, right, we conclude that f is strictly increasing if and only if g, I'll use if and only if shorthand, right, g is strictly decreasing. And that concludes our proof.